When we say that the speed of light is not just fast, but built into the structure of reality, we are making a claim that goes far beyond astronomy or optics. We are saying that the universe itself is constructed around this number, that space, time, energy, and matter all take their shape from it. To understand this, we have to let go of the everyday idea that speed is simply how quickly something moves from one place to another. In the deeper fabric of the cosmos, speed is not merely motion. It is a measure of how reality allows events to be connected. Before light entered the story, physics was guided by common sense. Space was thought to be a fixed stage, time a universal clock ticking the same for everyone. Motion was relative, and speeds simply added together. If you threw a ball forward while running, the ball's speed increased by the speed of your run. This logic worked perfectly for centuries, and it shaped how humans understood the universe. Nothing hinted that there was a maximum speed, let alone a fundamental one. Light changed everything. When scientists began measuring the speed of light carefully, they found something unsettling. No matter how fast the observer was moving, the measured speed of light stayed the same. Whether you were standing still, riding a train, or moving through space at incredible speeds, light always traveled at exactly the same rate. This was not a flaw in instruments or an error in experiments. It was reality refusing to behave the way intuition demanded. This forced a profound realization. If light's speed never changes, then something else must, and that something was space and time themselves. The speed of light is not simply how fast light travels through space. It is the rate at which space and time are linked together. It tells the universe how distance and duration relate to one another. Once this is understood, light speed stops being a property of light and becomes a property of spacetime. Imagine removing all matter, all stars, all particles, even light itself. What remains is spacetime, the stage on which reality unfolds. Embedded in that stage is a conversion factor between space and time. That factor is the speed of light. It tells us how many units of space correspond to a unit of time. It is as fundamental as the number of dimensions in space or the direction of time's flow. This is why light speed appears in equations that have nothing to do with light. It shows up in formulas for energy, mass, gravity, and causality. It is not there because light is involved, but because spacetime is involved. Whenever the universe needs to translate time into distance or distance into time, it uses the speed of light. One of the most striking consequences of this is that time itself becomes flexible. If you move faster through space, you move more slowly through time. This is not metaphorical language. Clocks carried by fast, moving objects actually tick more slowly compared to clocks at rest. This happens not because of mechanical effects or observational tricks, but because spacetime adjusts itself to preserve the speed of light. The universe is not allowing objects to experience different light speeds. Instead, it reshapes time so that light's speed remains unchanged for everyone. That alone tells us that light speed is not negotiable. It is enforced by the geometry of reality. Distance behaves the same way. Objects moving close to light speed becomes shorter in the direction of motion. Space compresses. Again, this is not a visual illusion or a measurement error. It is a physical change. Space itself contracts to maintain the cosmic rule. These effects would be absurd if light speed were just a fast, moving particle or wave. But they make perfect sense if light speed is a structural constant of spacetime. Reality bends itself rather than violate that limit. Another clue lies in causality, the idea that causes come before effects. The speed of light is the maximum speed at which cause and effect relationships can propagate. If something happens, its influence cannot spread faster than light. This is not a technical limitation. It is a safeguard for logical order in the universe. If signals could travel faster than light, then, in some frames of reference, effects would occur before causes. Events could influence their own past. The distinction between before and after would collapse. The universe avoids this chaos by embedding a speed limit into its structure. This limit defines what events can possibly influence one another. It carves spacetime into regions of can affect and can never affect. These regions exist whether or not light is present. They are part of the geometry of reality itself. In this sense, light does not set the speed limit. Spacetime does. Light simply travels at that limit because it has no mass. It follows the natural contours of spacetime without resistance. Massive objects cannot do this. Their mass ties them to slower paths through spacetime. As they accelerate, they require more and more energy to change how they move through time and space. This resistance is not mechanical friction. It is geometric resistance. Spacetime does not easily allow massive objects to approach its fundamental speed. The closer an object gets to light speed, the more extreme spacetime's response becomes. Time slows dramatically. Lengths shrink severely. Energy requirements rise steeply. These effects are not warnings or punishments. They are consequences of trying to move through spacetime in a way that contradicts its structure. Richard Feynman emphasized that mass and energy are deeply connected. When you push an object faster, you are not merely increasing its velocity. You are increasing its energy content. That added energy contributes to the object's inertia, making further acceleration harder. Near light speed, this process becomes runaway. Every added bit of energy increases resistance to acceleration. This is why light speed is unreachable for objects with mass. Not because engines are weak, but because spacetime geometry refuses to cooperate. The universe does not provide a path that allows mass to move at that rate. Light, having no mass, moves entirely through space, and not through time in the same way massive objects do. From light's perspective, if such a perspective could exist, no time passes at all. This is another indication that light speed is not just motion through space, but a special trajectory through spacetime itself. When physicists describe spacetime diagrams, light rays always appear at the same angle. That angle is fixed. It does not depend on the observer. It defines the structure of spacetime diagrams the same way vertical defines time and horizontal defines space. Light speed is woven into the very language physicists use to describe reality. Even gravity respects this limit. Changes in gravitational fields propagate at the speed of light. If the sun were to vanish, Earth would not instantly fly away. The information that gravity has changed would travel outward at light speed. This shows that even the shape of spacetime itself cannot update faster than this fundamental rate. Modern physics treats the speed of light as a conversion constant rather than a measured property. In many systems of units, it is set to 1. This is not a convenience. It reflects the understanding that space and time are two aspects of a single entity. Light speed is the bridge between them. When we say it is built into reality, we mean that without this constant, the universe would not function coherently. There would be no stable cause and effect, no consistent geometry, no reliable ordering of events. The speed of light is the thread that stitches the universe together. It also explains why attempts to exceed light speed feel unnatural and impossible. Faster. then light motion is not merely faster travel. It is an attempt to move outside the permitted structure of spacetime. It is like trying to move north of the North Pole. The direction simply does not exist. This is why light speed remains the same regardless of the observer's motion. Observers are not measuring light incorrectly. They are embedded in spacetime, and spacetime enforces the rule universally. Everyone agrees on the limit because the limit is not relative. It is absolute. In everyday life, we do not notice this because we move so slowly compared to light speed. Time dilation and length contraction are tiny at human speeds, but their existence, confirmed by countless experiments, reveals the hidden architecture of reality beneath our senses. Satellites in orbit experience time differently than clocks on Earth. Particle accelerators must account for relativistic mass increases. GPS systems would fail without corrections based on light speed and spacetime geometry. These are not theoretical curiosities. They are practical consequences of light speed being foundational. The universe does not treat light as special because it shines or illuminates. It treats light as special because it follows the deepest rules of spacetime without deviation. Light reveals the structure of reality because it is shaped by that structure more purely than anything else. To say that light speed is built into reality is to say that it is part of the universe's operating system. It governs how information flows, how time unfolds, how distances are measured, and how energy behaves. It is not an emergent feature, it is a foundational one. This realization changes how we see the cosmos. The universe is not a collection of objects moving through empty space. It is a dynamic network of events connected by spacetime, with light speed defining the maximum rate at which those connections can exist. And that is only the beginning. In the second half, this idea will be pushed further into how this built-in limit reshapes our understanding of motion, energy, and why reality itself seems designed to prevent anything from outrunning light. The idea that time and space themselves change in order to protect the speed of light is one of the most unsettling discoveries in human thought. It tells us that the universe does not treat time as a rigid, ticking clock or space, as an unchanging container. Instead, both are flexible, responsive, and deeply interconnected. They are not passive backgrounds where events happen. They are active participants that reshape themselves to enforce one fundamental rule. The speed of light must remain the same for everyone. To appreciate how radical this is, it helps to start with how humans naturally think. In everyday life, time feels absolute. 1 second feels the same today as it did yesterday. Space feels solid and reliable. A meter is a meter no matter who measures it. These assumptions are so deeply ingrained that questioning them feels almost absurd. Yet the universe does not share our intuition. When experiments showed that the speed of light is constant for all observers, physicists faced a dilemma. According to classical thinking, speeds should add. If you move toward a beam of light, you should measure it as moving faster. If you move away, you should measure it as slower. But this never happens. Light stubbornly refuses to change its speed. No matter how you move, no matter how fast you go, light always outruns you at the same rate. Something had to give. Either our understanding of motion was wrong, or our understanding of space and time was wrong. The universe chose the second option. Instead of allowing light's speed to vary, reality adjusts time and space. This adjustment is not subtle or philosophical. It is precise, mathematical, and experimentally verified. Time literally slows down for objects in motion. Space literally contracts in the direction of motion. These changes are not apparent at low speeds, which is why they escape notice for so long. But as speeds increase, the effects become impossible to ignore. Imagine two identical clocks. One stays on Earth, the other is placed on a fast, moving spacecraft. When the spacecraft returns, its clock shows less time has passed. This is not because the clock malfunctioned. It is because time itself flowed differently along its path. The moving clock experienced less time than the stationary one. Time was stretched, bent, and reshaped. This phenomenon, known as time dilation, exists for a single reason: to ensure that light's speed remains constant. If time did not slow down for moving observers, they would measure light at different speeds. Instead, time adjusts so that light behaves identically in all frames of reference. Space undergoes a similar transformation. Objects moving at high speeds shrink along the direction of motion. A ruler carried on a fast, moving spacecraft becomes shorter from the perspective of someone at rest. Again, this is not an illusion or a measurement trick. The object itself is physically shorter in that direction. This length contraction exists for the same reason as time dilation. It is spacetime's way of preserving the cosmic speed limit. By shrinking distances and slowing clocks, the universe ensures that light travels the same distance in the same amount of time for every observer. What makes this even more profound is that these effects are symmetrical. From the spacecraft's point of view, it is at rest, and it is Earth that is moving. From that perspective, Earth's clocks run slow, and Earth's rulers are contracted. There is no privileged observer. Reality reshapes itself consistently for all. This symmetry reveals a deeper truth. There is no absolute time ticking away in the background. There is no universal now, shared by everyone. Time is personal. Each observer carries their own version of time, shaped by their motion through space. Space, too, loses its absoluteness. Distances depend on the observer's motion. Two events that are simultaneous for one observer may not be simultaneous for another. The order of events can even change depending on how fast someone is moving, as long as those events are not causally connected. This is not a failure of reality. It is reality functioning exactly as it must to protect the speed of light. The speed of light acts like a fixed anchor point in spacetime. Everything else adjusts around it. Instead of light adapting to space and time adapt to light. This reversal of perspective is one of the greatest conceptual shifts in physics. At the heart of this lies the union of space and time into a single entity, spacetime. Space and time are not separate ingredients of the universe. They are different aspects of the same structure. Motion through one affects motion through the other. An object always moves through spacetime at a constant combined rate. If it moves slowly through space, it moves quickly through time. If it moves quickly through space, it moves slowly through time. This balance is not negotiable. It is enforced by the geometry of spacetime itself. Light occupies a unique position in this structure. It moves through space at the maximum possible rate, which means it does not move through time in the same way massive objects do. This is why light experiences no passage of time between emission and absorption. From the universe's perspective, light's path is extreme but allowed. Massive objects cannot follow that path. As they accelerate, spacetime resists. Time slows down more and more, lengths shrink more and more, and energy demands rise sharply. These effects are spacetime's response to an object attempting to approach the forbidden trajectory. What is remarkable is that these changes are not imposed externally. There is no cosmic policeman enforcing the rules. The rules are consequences of the structure itself. Just as the angles of a triangle behave differently on a curved surface, time and space behave differently in a universe with a fixed speed limit. This becomes especially clear when we consider simultaneity. In everyday life, we assume that if two events happen at the same time, they happen at the same time for everyone. But in a relativistic universe, simultaneity depends on motion. Two observers moving relative to each other will disagree on whether events are simultaneous. This disagreement is not due to faulty clocks or communication delays. It arises because time itself is sliced differently for each observer. There now, surfaces tilt relative to each other in spacetime. This tilting is exactly what is needed to preserve the speed of light for all. If simultaneity were absolute, light's speed would vary between observers. By giving up universal simultaneity, the universe keeps light speed invariant. Once again, time sacrifices its absoluteness to protect a deeper rule. These ideas sound abstract, but they have concrete consequences. Particle accelerators rely on time dilation to function correctly. Particles traveling near light speed live longer than they would at rest. This extended lifetime allows them to be studied. Without time dilation, many experiments would be impossible. Even technology depends on these effects. GPS satellites orbit Earth at high speeds and experience weaker gravity. Their clocks tick at different rates compared to clocks on the ground. If engineers did not account for relativistic time changes, GPS positioning would drift by kilometers each day. These practical realities confirm that time and space are not fixed. They respond dynamically to motion and gravity. They are elastic, not rigid. What makes this even more astonishing is that these changes are not arbitrary. They follow precise mathematical relationships. The universe does not distort time and space randomly. It does so in the exact way needed to keep the speed of light constant. This suggests that light speed is not just another constant among many. It is a structural constraint. It defines how spacetime is allowed to behave. Any universe with a finite, invariant speed would exhibit similar properties. In that sense, relativity is not just about our universe. It is about what any logically consistent universe must look like if it has a maximum signal speed. The flexibility of time and space also explains why faster than light travel is so problematic. To exceed light speed, spacetime would need to contort itself in impossible ways. Time ordering would break down, cause and effect would become ambiguous. The universe would lose its internal consistency. By allowing time and space to bend, but only within strict limits, the universe maintains order. It permits extraordinary effects without descending into chaos. Time can slow, space can shrink, but the speed of light remains untouched. This reveals a universe that is not fragile, but robust. Pushed to its extremes, BSORBS spests stress by reshaping its geometry rather than breaking its rules. Instead of allowing contradictions, it adjusts its foundations. From a human perspective, this feels counterintuitive because we experience only a narrow slice of possible motions. We are slow, moving creatures in a low-gravity environment. Time and space appear stable to us because the conditions that reveal their flexibility are extreme. But the flexibility is always there, hidden beneath the surface. Once seen, it cannot be unseen. Time is no longer a universal river flowing the same for everyone. Space is no longer an absolute grid. They are dynamic, relational, and responsive, and all of this happens for one reason: to preserve the invariance of light speed. The speed of light is the spine around which spacetime is built. Time and space curve, stretch, and compress to uphold it. They do so silently and consistently, shaping every motion, every interaction, and every moment in the universe. In accepting this, we are forced to revise our deepest intuitions. Reality is not what it appears to be at human scales. Beneath our experience lies a structure that prioritizes consistency over comfort, logic over intuition. Time and space are not the rulers of reality. They are its servants, and they serve one master, the unchanging speed of light. The resistance of mass to motion becomes one of the most revealing features of the universe when objects are pushed to extreme speeds. At everyday scales, mass feels simple. A heavier object is harder to push than a lighter one, but once it is moving, it keeps moving unless something stops it. This idea, rooted in classical physics, works perfectly well for cars, airplanes, and even planets. But as speed increases and begins to approach the speed of light, mass reveals a far deeper and stranger behavior, one that exposes how motion is woven into the fabric of spacetime itself. In ordinary experience, acceleration feels like a straightforward process. Apply a force, gain speed. Apply more force, gain more speed. There seems to be no fundamental limit, only practical ones like engine power or friction. Classical physics assumes that speed can increase indefinitely if enough force is applied. There is no built-in resistance tied specifically to velocity itself. But the universe does not agree with this assumption. As objects accelerate closer to the speed of light, they do not behave like classical objects anymore. Each increase in speed becomes harder than the last. The object resists acceleration more strongly, even if the applied force remains the same. This resistance is not caused by friction, air, or any external medium. It comes from the object's own mass interacting with spacetime. This phenomenon is often misunderstood as mass increasing with speed. While modern physics prefers to describe this effect differently, the core insight remains the same. Mass and motion are deeply entangled. As an object moves faster, its inertia grows. It becomes increasingly difficult to change its state of motion. This resistance is not accidental. It is spacetime's way of enforcing the cosmic speed limit. To understand why this happens, it helps to abandon the idea that motion is only movement through space. In relativity, motion is movement through spacetime. Every object follows a path called a world line, tracing its history through both space and time. An object at rest moves only through time. An object in motion moves through both space and time. There is a fixed total rate at which objects move through spacetime. If more of that motion is directed through space, less is available for motion through time. This is not a choice made by the object. It is a structural feature of the universe. As an object accelerates, it attempts to redirect more of its spacetime motion into the spatial dimensions. But spacetime resists this redirection. The closer the object gets to light speed, the more extreme that resistance becomes. Mass is the measure of how strongly an object resists changes to its motion through spacetime. It is not merely a quantity of matter. It is a property that describes how an object responds when you try to accelerate it. At low speeds, this resistance appears constant. At high speeds, it grows dramatically. This growth is not linear. Each additional fraction of speed requires disproportionately more energy than the last. Near the speed of light, the required energy skyrockets. Even an enormous increase in energy produces only a tiny increase in speed. This is why no amount of force can push a massive object to light speed. The resistance does not come from a wall or barrier. It comes from the object's own inertia, amplified by relativistic effects. Richard Feynman emphasized that energy and mass are two sides of the same coin. When you accelerate an object, you are adding energy to it. That energy does not simply disappear into motion. It becomes part of the object's physical reality. It contributes to its inertia. In this sense, an object moving at high speed is not the same object it was at rest. It contains more energy, and that energy behaves like mass. The object becomes harder to accelerate, not because it is heavier in a traditional sense, but because it is more energetically dense in spacetime. This leads to a profound realization: speed itself contributes to inertia. The faster an object moves, the more it resists further acceleration. This feedback loop ensures that light speed remains unattainable. As speed increases, resistance increases faster. The universe closes the gap faster than the object can approach the limit. This behavior is not arbitrary. It is a natural outcome of how spacetime is structured. Light travels at the maximum allowed speed because it has no mass. It does not resist acceleration in the same way massive objects do. It follows a path through spacetime that massive objects cannot access. Massive objects are constrained to slower trajectories. They can approach the light-like path, but never reach it. The resistance grows infinitely as they get closer. This infinite resistance is not something we encounter directly in everyday life, which is why it feels counterintuitive. At human speeds, relativistic effects are negligible. The resistance increase is so small that it goes unnoticed. But in particle accelerators, where particles are pushed to near light speeds, this resistance dominates behavior. In these machines, particles are given enormous amounts of energy. Yet despite this, their speeds increase only marginally once they are close to light speed. Instead of moving faster, they become harder to deflect, harder to stop, and harder to accelerate further. Their resistance to change becomes extreme. This is not a failure of engineering. It is a demonstration of fundamental physics. The concept of mass resisting motion also reshapes how we understand force. In classical physics, force equals mass times acceleration. Mass is constant. Acceleration changes. In relativity, this simplicity breaks down. The relationship between force and acceleration becomes more complex because inertia itself depends on speed. At high velocities, applying force does not produce the expected acceleration. The object responds sluggishly, as if it were embedded in thick spacetime. This sluggishness is not due to fatigue or loss. It is due to the geometric constraints of the universe. The object is not just being pushed through space. It is being asked to reorient its motion through spacetime. That reorientation becomes increasingly difficult as the object approaches the light speed boundary. This also explains why massless particles behave so differently. Photons do not resist acceleration because they cannot be accelerated in the same sense. They always move at light speed. Their motion through spacetime is fixed. They do not have the freedom to redistribute motion between space and time the way massive objects do. Mass, then, is what anchors objects to slower than light trajectories. It ties them to time. The more mass an object has, the more strongly it is bound to moving through time rather than space. Accelerating such an object requires peeling it away from its natural flow through time, and spacetime resists this peeling. This resistance is not a force acting against motion. It is a consequence of geometry. Spacetime is structured in such a way that massive objects prefer certain paths. Deviating from those paths requires energy, and the closer the deviation comes to a forbidden path, the more energy is required. This perspective also clarifies why mass and energy are interchangeable. Energy can create mass, and mass can release energy. They are not separate substances. They are manifestations of how much an object resists changes to its motion through spacetime. When you accelerate an object, you are increasing its energy, and therefore increasing its resistance to further acceleration. This self-limiting process ensures that no finite energy source can ever overcome the infinite resistance at light speed. This has profound implications for travel, technology, and imagination. Science fiction often treats faster than light travel as a matter of powerful engines or exotic fuels. But the true obstacle is not power. It is the nature of mass itself. As long as an object has mass, it carries with it this built-in resistance. No engineering solution can remove it without fundamentally changing what the object is. To reach light speed, an object would have to shed its mass entirely. But doing so would transform it into something else altogether. This is why attempts to imagine accelerating humans or spacecraft to light speed run into insurmountable problems. The closer such objects get, the more energy they would require, not just practically, but conceptually. The energy demands do not grow large, they grow without bound. The universe does not simply say no. It makes the attempt meaningless. The goal recedes infinitely, never quite reachable. This behavior also preserves causality. If massive objects could reach or exceed light speed, the order of cause and effect could be violated. Signals could arrive before they were sent. The logical structure of reality would unravel. The resistance of mass acts as a safeguard, preventing such contradictions. In this sense, mass is not a limitation imposed on objects. It is a stabilizing feature of the universe. It keeps motion within bounds that preserve coherence and order. The deeper one looks, the clearer it becomes that mass is not merely something objects have. It is something objects do. It is how they interact with spacetime. It is the expression of their reluctance to be pushed into forbidden regions of motion. This reframes inertia from a passive property into an active relationship. Objects are not stubborn by nature. They are obedient to spacetime geometry. Their resistance is not defiance. It is alignment with the structure of reality. As speeds increase, this alignment becomes more pronounced. Spacetime tightens its grip. Motion becomes more constrained. Energy becomes more concentrated. The universe reveals that speed is not free. By the time an object approaches light speed, it is no longer meaningful to think in terms of classical motion. The object exists in a regime where mass, energy, space, and time are inseparable. Every attempt to push further is met with overwhelming resistance, not from the outside, but from within the object's own physical identity. This is why light speed is not just hard to reach. It is unreachable. Mass ensures this not through force, but through structure. It turns acceleration into an asymptote, a limit that can be approached endlessly but never crossed. And in doing so, mass reveals itself as one of the universe's most elegant mechanisms, a quiet enforcer of cosmic order, ensuring that motion remains consistent with the deepest rules of spacetime. The closer an object moves toward the speed of light, the more the universe reveals a strange and unforgiving truth. Energy does not scale gently with speed. It explodes. What begins as a manageable requirement quickly turns into an insatiable demand, one that no finite source could ever satisfy. This is not a limitation of technology or engineering. It is a consequence of how reality itself is constructed. At low speeds, energy behaves politely. Doubling your speed roughly doubles the energy needed. This aligns perfectly with everyday experience. A bicycle needs more effort to go faster. A car burns more fuel at higher speeds. An aircraft demands enormous power to push past air resistance. These increases feel steep, but they remain finite and predictable. Nothing suggests an absolute barrier. But as speed increases further, something unexpected happens. The relationship between speed and energy begins to curve. Each additional increase in speed requires disproportionately more energy than the last. This curvature grows steeper the closer the object comes to light speed. Eventually, the curve rises almost vertically. At that point, speed barely increases at all, no matter how much energy is added. This is where classical intuition breaks completely. In the relativistic universe, energy is not just the fuel of motion. It becomes part of the object itself. When energy is added to accelerate an object, that energy does not simply vanish into velocity. It contributes to the object's inertia. The object becomes harder to accelerate precisely because it contains more energy. This creates a feedback loop. To go faster, you must add energy. Adding energy increases resistance to further acceleration. That increased resistance demands even more energy for the same speed gain. As light speed approaches, this loop becomes extreme. Near the speed of light, the amount of energy required for even the smallest increase in speed becomes enormous. To actually reach light speed would require infinite energy. This is not a dramatic exaggeration. It is a mathematical and physical statement. Infinite energy means no amount of fuel, no engine, no technology could ever suffice. The universe does not hide this fact. It advertises it openly in its equations. Energy and momentum grow without bound as velocity approaches light speed. The numbers do not plateau, they do not level off, they diverge, they race toward infinity. This divergence is not an accident of mathematics. It is how the universe protects its fundamental limit. This infinite energy requirement is deeply tied to the structure of spacetime. Speed is not just movement through space. It is a redistribution of motion between space and time. As an object accelerates, it trades motion through time for motion through space. But this trade is not unlimited. At rest, an object moves fully through time. As it accelerates, some of that motion is redirected into space. The faster it goes, the less motion remains through time. At light speed, there would be no motion through time left at all. That final step is forbidden for massive objects. To remove the last fraction of time, like motion, would require an infinite reconfiguration of the object's spacetime trajectory. Energy is the currency required to perform that reconfiguration, and the price becomes infinite as the limit is approached. This is why adding energy stops being effective. Energy is being spent not on increasing speed, but on fighting the geometric resistance of spacetime itself. Particle accelerators demonstrate this reality with brutal clarity. In these machines, particles are pushed to extraordinary energies. Yet once they are close to light speed, their velocities barely change. Instead, the added energy manifests in other ways. The particles become harder to bend, harder to slow down, harder to contain. Their momentum increases dramatically, but their speed remains stubbornly fixed just below the limit. This is not a flaw in the machines. It is spacetime refusing to allow a massive object to cross into forbidden territory. The energy does not disappear. It reshapes the particle's behavior. It increases its inertia. It deepens its interaction with fields. But it does not grant access to higher speeds. This behavior reveals a crucial insight. Speed is cheap at first, but infinitely expensive near the top. The universe front loads accessibility and back loads impossibility. This is why light, which has no mass, occupies such a unique position. Light does not require energy to accelerate to light speed. It simply exists at that speed. Energy determines its frequency, not its velocity. Light can have more or less energy, but it never moves faster or slower. Massive objects are different. Their energy is tied to their motion in a way that inevitably leads to divergence near light speed. Richard Feynman emphasized that mass and energy are interchangeable. This equivalence explains why energy added to an object behaves like mass. As energy accumulates, it contributes to inertia. The object resists acceleration more strongly because it has become, in a very real sense, more massive. This does not mean the object gains rest mass in the traditional sense, but the distinction becomes irrelevant at high speeds. What matters is resistance to acceleration. Energy enhances that resistance. This insight reframes the problem of reaching light speed. It is not that engines are too weak. It is that energy itself becomes the obstacle. The very tool used to accelerate becomes the thing that prevents further acceleration. Every unit of energy added increases the difficulty of adding the next unit. This runaway effect ensures that no finite process can ever complete the journey to light speed. The requirement of infinite energy also protects the universe from paradoxes. If finite energy could produce infinite speed, causality would collapse. Effects could precede causes. Information could arrive before it was sent. The logical order of events would unravel. By demanding infinite energy, the universe ensures that such scenarios remain purely hypothetical. They are mathematically imaginable, but physically unreachable. This limit is not a boundary in space. It is a boundary in possibility. Objects can approach it endlessly, but they never arrive. The closer they get, the more reality pushes back. What makes this especially striking is that the universe does not slow objects down with friction or drag. There is no external force resisting motion. The resistance arises internally from the relationship between energy, mass, and spacetime. Even in the vacuum of space, with no particles to collide with, the energy cost of acceleration near light speed becomes prohibitive. The obstacle is not the environment, it is existence itself. This realization also explains why faster than light travel remains speculative and problematic. Any proposal that claims to bypass the energy barrier must fundamentally alter spacetime itself, not just push objects harder. It must change the geometry that enforces the limit. Without such a change, energy requirements will always diverge. No clever engineering can flatten that curve. The infinite energy requirement is not a bug in the universe. It is a feature. It ensures consistency. It maintains order. It keeps cause and effect intact. It also reveals a universe that values structure over convenience. The laws of physics are not designed to accommodate ambition. They are designed to preserve coherence. As humans, we often think of limits as challenges to overcome. But some limits are not obstacles, they are foundations. The speed of light is one such foundation. Energy's divergence near that speed is how the universe tells us that the foundation cannot be crossed. This understanding reshapes how we think about progress. It suggests that advancement is not about pushing harder in the same direction, but about understanding the structure of reality more deeply. The path forward is not brute force, but insight. The infinite energy barrier stands as a reminder that the universe is not infinitely permissive. It allows remarkable flexibility, but only within strict bounds. Those bounds are not arbitrary. They are woven into the relationship between energy, mass, space, and time. When an object accelerates toward light speed, it is not racing toward a finish line. It is climbing a curve that steepens without end. Each step upward costs more than the last, until the cost becomes infinite. And infinite cost means the journey can never be completed. This is why the speed of light remains untouched, not because it is guarded by force, but because it is protected by mathematics, geometry, and the deep equivalence of mass and energy. The universe does not slam the door shut. It simply makes the door infinitely heavy. And in doing so, it ensures that light speed remains what it has always been, not just the fastest speed possible, but the speed that defines what is physically possible at all. The speed of light is not only a limit on motion, it is a limit on meaning. It defines how the universe allows events to be connected, how information flows, and how cause leads to effect. Without this limit, reality would not merely behave differently, it would lose its logical structure. What we call causality, the simple idea that causes come before effects, survives only because the universe enforces a maximum speed at which influence can travel. In everyday life, causality feels obvious. You strike a match, then it ignites. You speak, then someone hears you. The order of events feels absolute and unquestionable. But this certainty is an illusion born from slow speeds and short distances. At the deepest level, causality is not guaranteed by common sense. It is guaranteed by the speed of light. Every interaction in the universe is a transfer of information. When two particles interact, when gravity pulls, when light reaches your eyes, information is moving. The speed of light is the maximum speed at which that information can travel. It defines how quickly one part of the universe can know about something happening elsewhere. If this limit did not exist, or if it could be exceeded, the concept of before and after would lose its universal meaning. To understand why, we need to confront one of the strangest consequences of relativity. Time order depends on motion. Two observers moving relative to each other can disagree about the order of events, as long as those events are not causally connected. This disagreement is not due to perception or delay. It is built into the structure of spacetime. Normally, this does not cause problems because the speed of light creates a strict boundary. Events that can influence each other are connected by signals traveling at or below light speed. Events that cannot influence each other lie outside that boundary. The universe is neatly divided into what can matter to you and what cannot. This division is not philosophical. It is geometric. Every event in spacetime creates a region of possible influence. Signals can spread outward from that event, but only at light speed or slower. This creates a cone-like structure in spacetime that defines the future of that event. There is also a past cone, defining what could have influenced it. Anything outside these regions is causally disconnected. These structures exist whether or not light is present. They are properties of spacetime itself. Light simply traces their edges. As long as nothing travels faster than light, causality is safe. Causes always precede effects in every frame of reference. Observers may disagree on timing, but they will never disagree on what caused what. The moment faster than light motion is allowed, this protection collapses. If information could travel faster than light, then there would exist frames of reference in which an effect occurs before its cause. This is not a hypothetical curiosity. It is a direct consequence of how time and space transform between observers. An event that is later, in one frame, can become earlier, in another if the separation between events is faster than light. This means a message could be received before it was sent. A signal could arrive in the past of its own origin. This is not merely strange, it is catastrophic for logic. Once effects can precede causes, contradictions become unavoidable. You could send information that prevents itself from being sent. You could receive answers to questions before asking them. You could influence events that supposedly already happened. The universe avoids these paradoxes not by forbidding imagination, but by forbidding the physical conditions that would allow them. It enforces a universal speed limit on information. This is why the speed of light is often described as the speed of causality. It is not primarily about photons. It is about the maximum rate at which the universe allows cause and effect relationships to propagate. Gravity obeys this limit. Changes in gravitational fields travel at light speed. If the sun were to suddenly disappear, Earth would not instantly fly away. It would continue orbiting for about 8 minutes, until the information that gravity had changed arrived. This delay is not due to weakness or inefficiency. It is a safeguard. It ensures that the universe updates itself consistently without contradictions. Electromagnetism obeys this limit. Quantum interactions obey it in subtle ways. Even entanglement, often misunderstood as faster than light communication, does not allow usable information to be transmitted beyond this boundary. Every known interaction respects the same speed limit because they all participate in the same causal structure. Richard Feynman emphasized that the laws of physics are deeply concerned with consistency. They are not arbitrary rules, but systems designed to prevent contradiction. The speed of light is one of the most important tools in that system. It ensures that the universe has a well-defined order of events, not an absolute order that everyone agrees on, but a consistent order that never contradicts itself. Time in relativity is flexible. Different observers slice spacetime differently. Their nows do not align. But despite this flexibility, causality remains rigid. No observer ever sees an effect happen before its cause if the signal connecting them travels at or below light speed. This balance is delicate. Time is allowed to bend, stretch, and reorder itself, but only within the boundaries that preserve causal consistency. The speed of light is the boundary that makes this possible. Without it, spacetime would not merely be flexible. It would be incoherent. This reveals something profound about the universe. It is not constructed to maximize freedom of motion. It is constructed to maximize logical consistency. Some things are allowed to vary time rates, lengths, simultaneity, but other things are non-negotiable. Causality is one of those non-negotiables. The universe does not permit any process that would undermine the concept of cause and effect. Faster than light information would do exactly that. So such processes are excluded by the structure of spacetime itself. This is why proposals for faster than light travel always face severe conceptual problems. Even when they appear mathematically clever, they struggle to preserve causality. They require exotic conditions, negative energy densities, or spacetime distortions that push against the very rules that make physics coherent. The difficulty is not technological, it is logical. To allow faster than light signals is to allow time loops, paradoxes, and contradictions. The universe does not merely discourage these outcomes, it structurally prevents them. This prevention is elegant. Instead of banning faster than light motion explicitly, the universe makes it unnecessary. It embeds causality into geometry. It ensures that the fastest possible trajectory through spacetime aligns exactly with the boundary of causal influence. Light follows that boundary because it has no mass. It is the purest messenger of cause and effect. Massive objects move inside that boundary, slower, safer, bound to a strict temporal order. This is why light speed appears everywhere in physics. It is not a detail. It is the organizing principle that keeps reality from tearing itself apart. When we talk about the collapse of the mind in confronting these ideas, it is not because they are flashy or dramatic. It is because they force us to accept that the universe cares about logic more than intuition. Reality is not designed around human experience. It is designed around internal consistency. The speed of light is the glue that holds that consistency together. It defines the maximum speed at which the universe can update itself. It ensures that information does not outrun causation. It guarantees that effects never appear from nowhere, unanchored from causes. Even time travel fantasies struggle against this constraint. Any scenario that allows backward causation must confront the same barrier. Either causality is violated, or the scenario becomes consistent in ways that eliminate free manipulation of the past. Again, the universe protects itself. This protection is not authoritarian. It is structural. Just as geometry prevents certain shapes from existing, spacetime prevents certain sequences of events from occurring. The speed of light is not a speed limit imposed on objects. It is a rule imposed on relationships. It tells the universe how events are allowed to relate to one another across space and time. Without it, there would be no reliable notion of influence, no stable chains of cause and effect, no meaningful distinction between past and future. The universe would become a logical blur. That it does not is one of the deepest facts of existence. The speed of light ensures that while time may be relative, causality is not. While observers may disagree on when something happened, they will never disagree on why it happened. This is the final and perhaps most profound reason the speed of light is the ultimate limit. It is not there to frustrate exploration or limit ambition. It is there to ensure that reality makes sense, and without it, sense itself would collapse.